So forces, as they apply to circular motion, really are no different than forces that apply to linear or stationary motion, except now these objects are moving in a circle. When we're talking about the acceleration involved, we can talk about the centripetal acceleration, and the fact that we talked about that in Unit 1 actually leads us to some specific formulas we can use when we're talking about forces in circular motion. So one way the way that these forces get used in real life is if we look at a vehicle on a curve. We know, having driven on curves, that curves are not flat like shown there. They're banked towards the inside. Because Newton's first law of inertia says that this car, if no outside force acts on it, will want to continue straight on. However, if we bank the road towards the inside of the curve, we're actually creating a force of gravity that is slightly to the left in this case, which will help keep that car on the road, especially when it's icy and the friction between the tires and the road is less than if it's dry. When we deal with forces in circular motion, the key thing is that the centripetal acceleration and the centripetal force is towards the center of the circle. And this force that we're dealing with is no different than any other applied force: gravity, friction, air resistance, tension, etc. The formulas, as we can see here, very similar to those of calculating centripetal acceleration. The only difference is now all of these have a mass component to the formula, because force equals mass times acceleration. We're just substituting in that piece of the acceleration equation. How does it look when we do it? Car of mass 1100 kg negotiates a level curve at a constant speed of 22 meters per second. Curve has a radius of 85 meters. Draw an FBD of the car. So, as we know with any free body diagram, the object is just a box. Thinking about the forces, well, we have gravity, obviously. We have a normal force exerted by the load up on the car. We have no tension coming from above this car. We will, for the moment at least, ignore static or kinetic friction, as well as air resistance, as well as the applied force. Because what matters to us is the fact that this car is on a curve. It is experiencing centripetal force towards the inside of the curve. Now, is this car turning right or turning left? We don't know. But if the car is turning to the right, then the centripetal force is to the right, and we would call that Fc. And that would be the free body diagram. In B, to now determine the magnitude of the force that must be exerted to keep the car from skidding sideways, this is the magnitude of the centripetal force. So that's what you've been asked to find. What do we know? We know we have a mass of 1100 kg. We know we have a speed of 22 meters per second. And we have a radius of 85 meters. Looking at the formulas, that first one is going to be the most useful to us right now. Go ahead and substitute in. Mass is 1100. V is 22, and that's 22 squared. R is 85. going to go ahead and do 22 squared before I do anything else. That's 484. From here, we can one-stop shop this. Gives us 6,264. As usual with any calculation, sig figs do come into play. All of the first-hand information had 2 sig figs, so we'll take this to 2 sig figs. It'll be 6,300. Units of force would be newtons. And since I asked just for the magnitude of the force, we're not looking for the direction. We could have said that it's towards the center of the circle, but considering I didn't give you any directions, that's why I just asked for the magnitude. Moving on, the minimum coefficient of static friction needed to keep the car on the road. So to get the coefficient of friction, we need to know the amount of static friction, which is going to be equal to the amount of the centripetal force pulling to the center. So static friction would be 6,300 newtons of friction that we need to equal that. The coefficient of friction would be mu. We don't know that. Everything else has remained the same. So when we're calculating out static friction, Fs equals mu s times the normal force but since we know that the normal force is the force of gravity, and since F equals ma, substituting graphically and specifically mg, we can write this equation differently, and instead of Fn, we can substitute m in mg. Now, I'm not going to define my variable for gravity because it is 9.8 meters per second squared. I'm just going to substitute in what we know. Static friction, 6,300 newtons. Mu s, we're trying to find that. Mass from before, 1,100 kgs. And g is 9.8. All I'm going to do here is I'm going to take my 1,100, multiply it by 9.8, gives me 10,780. To get mu by itself, divide both sides by 10,780. I'm going to go straight to the proper sig figs. It's going to need 2, which should give us a coefficient of friction of 0.58. And as before, coefficients of friction do not have units, so that is that. Moving on, we have a 0.52 kg mass rotating in a circle with a radius of 2 meters at a frequency of 3.00 hertz, and I want to know what's the centripetal force acting on the mass. So centripetal force is Fc. That's what we've been asked to find. We have mass of 0.52 kgs. We have radius of 2.0 meters. And a frequency, which is F, of 3.00 hertz. Going back to the equations, that one on the right is going to be the most useful to us. So FC equals 4 pi squared MRF squared. Substituting in, 4 is 4, pi is pi, M is 0.52, R is 2.0, F is 3.00, that is squared. Only thing I'm going to do in the next step, oh, I missed the squared on that pi. Only thing I'm going to do in this step is actually do the 3.00 squared at the end of that, which is 9. I can take that and one-stop shop it in the calculator. Should give me 369.5. And going straight to the proper number of sig figs. We've got 2 sig figs in 2 numbers, 3 sig figs in the other one. We always go with the smallest number of sig figs, so that'll be 2. So 369.5 will round to 370, and that's measured in newtons. Last example, we have a 662 kilogram Starlink satellite orbiting the Earth in a circular path with a radius of 6,780,000 meters. Yes, I fact-checked that. That is accurate. If the period of rotation of the satellite is 90 minutes, what is the force exerted on the satellite? So what is the force exerted? The centripetal force we've been asked to find. We have the mass, 662 kilograms. We have the radius, 6,780,000 meters. We have the period. Period is T, which is 90 minutes. The problem with this is we can't use 90 minutes in a scientific calculation. We need to go with standard units of seconds. So to convert minutes to seconds, we'll multiply by 60, which gives us 5,400 seconds. Looking at formulas, that one in the middle is going to be what we need. So FC equals 4 pi squared MR over T squared. Substituting in, 4 is 4, pi is pi, it's squared. Mass is 662. Radius, 6,780,000. And period is 5,400, and that is squared. All I'm going to do in the next step is actually do 5,400 squared. That is 29,160,000. To get the answer, we can do this all in one stop. Should give us just a hair over 6,076 newtons. But looking at sig figs, 3 in the mass, 3 in the radius, but only 1 in the time. 90 minutes is first-hand information. This final answer should have 1 sig fig, and then 6,076 would round to 6,000. And again, being force, we're going to measure that in newtons.